Thank you. So thanks again for organizing this wonderful conference. This is joint work with Ahuba Moalen, who's at HIT Israel, and I'm at UNSW Sydney. Okay. So let me motivate the talk by saying that buyers face financial constraints, and there is lots of evidence about that fact. And if you are into behavioral stuff, you can think of Richard Thaler telling you stories about how he has mental budgets, and that constrains how much he's willing to pay for some goods, how much he's well able to pay for some goods. But even if you disregard that, you can consider high-stake deals where the value for the goods to be allocated is large, very large relative to the buyer's liquid assets. Right? So you have, for instance, spectrum licenses. You can think of privatizations, mineral extraction rights, housing and other durable goods markets. So in Sydney, where I live, the median price of a house is $1.2 million, and you have to have 20% of the value of the house before even asking the bank for a loan. So that acts as a hard constraint, budget constraint. So, and sellers know it. So sometimes they don't take it into account, but sometimes they do. So for instance, in Google Key Auction platform, you have to specify not just your bid, but also a daily budget limit. So most of mechanism design ignores financial constraints from the part of the buyer. And we do it because it's relatively easy, or let me put it that way, another way, it gets very hard very quickly to consider financial constraints in mechanism design. But it's not inconsequential. So it's not the case that it's just a good assumption to have, and who cares about the assumptions when we get what we want. For instance, Chiangil showed that with private budget constraints, the revenue equivalence between the first price auction and the second price auction no longer holds. Okay, so in this talk, what I want to do is I want to talk about mechanism design, sort of an abstract environment of a mechanism design problem, and try to convince you that we have a sort of new take on that allows us to say something interesting about the implications of having budget constraints. Obviously, we are not the first to work on this. In fact, some of you on the audience have worked on this, but most of the previous work is focusing on single item selling mechanisms, so whereas we're going to allow for multiple items as well. Okay, so let me just straight ahead tell you with an example what sort of problem we can tackle. The seller is going to have two items, so there's only one buyer and one seller. The seller has two goods to allocate, so think of air freight routes between two major hubs. A is an alternative that allocates one of the licenses to a potential buyer. A prime signifies allocating both licenses to the buyer, and A naught is just the exclusion option. Okay. The buyer is going to have 4 different valuations. So V1 has 11, so has a value of 11 for A and a value of 16 for A prime. So think of V1 as a newcomer, a very small newcomer into the market, very low fixed cost, but because of its size, it cannot exploit complementarities between A and A prime. So it cannot exploit complementarities between having one route and having 2 routes. At the other extreme, you have V4. This is a legacy carrier. It has a heavy, large fixed cost. So the value for one item, for item A, one alternative, one license is just 6. But because it can exploit complementarities, massive complementarities, the value of having 2 licenses is 26. Okay. The buyer for the budget in this example is just going to be BL. The budget set for the buyer is going to be BL and BH. And both are private information. So valuations and budgets are private information. Okay? So in a picture, in the horizontal axis, what I have is the difference between getting 2 licenses and getting one license. And in the vertical axis, I have budgets. So each dot represents one type of buyer. Okay? So if the value difference is 5 and your budget is low, this is your point, and so on and so forth. Okay? So I have 8 types. If I want to solve this problem using the incentive compatibility constraints, I need 56 constraints, 56 equations plus 7, plus 8 participation constraints. So I will need to write 64 equations, inequalities to solve this. And, as Chang Tao know, I'm lazy. So I don't want to do that. It's too much work for me. So what I want to think of is something that looks like this. So it's an allocation graph where I have A prime, and A naught. And I want to see if I can endow this graph, this network, with quantities that that represent the edges. And I want to see if I can use this type of network instead of the 64 inequalities that I would have to work with. Okay, this is where I'm going to go. Yeah. So let me tell you the setting. The setting is very general, and I think this is an advantage of this paper because it will allow to tackle different problems. I only have I have a set of alternative A, and the only restriction is that it should be finite. Okay, I have. I'm not going to have a parameterized type space. I'm just going to say that VA is a valuation for A. Curly capital VA is the set of admissible valuations for A. And curly V is the set of valuations for this agent, right? So it's the set of functions that tell you how much this guy likes each alternative. Okay? And again, I'm not going to impose any constraints on what V looks like. The buyer also faces financial constraints. So capital B is a set of admissible budgets with typical element V. Okay? So typical elements of the alternative set are A prime, and so on and so forth. For the valuation, I have V prime, and so on and so forth. And for budgets, I have capital B's. Okay? Very simple stuff. I'm going to assume, as most of the literature does, that budgets are hard constraints. So in other words, a buyer with a type V, B who pays rho for alternative A has a utility equal to VA minus rho, so quasi-linearity is assumed here, as long as he pays an amount below his budget. If he pays an amount above his budget, his utility is going to be minus infinity. Okay? So that's the setting that I have. There's no other assumption on the model. Okay, so I need to impose, I'm going to use a direct mechanism first, and then I'm going to shift to nonlinear prices. A direct mechanism is what you think it is, a function f, an allocation function f, and a transfer function rho. Okay? In a world without budgets, without private budgets, we think of implementability as incentive compatibility. Okay? But in this world, implementability cannot be just incentive compatibility because I can force agents to pay an amount above the supremum of the budget set, and everyone is going to have minus infinity as a utility regardless of what they tell me. So the mechanism is trivially incentive compatible. So in order to talk about implementability, I'm going to talk about two things, and then another one. Budget feasibility and incentive compatibility. Okay? So budget feasibility says that for any type V, B, the amount that the mechanism asks the buyer to pay if he reports truthfully has to be below his budget. Okay? The mechanism is called incentive compatible if any affordable deviation for a type, for any type, is non-profitable. In other words, if your type is VB, telling the truth is weakly better off than lying and reporting any other type V prime, B prime, as long as reporting this fake type, V prime, B prime, is below your own budget. Okay, so the money that you have to pay is below your own budget. So any affordable deviation is not profitable for the buyer. Okay, so I have incentive compatibility and I have budget feasibility, and these are what I think of implementability. But then you're going to say you are not looking at revenue maximization, and that is true. I'm not looking at revenue maximization yet. So the problem could be vacuous. You just let the seller subsidize consumption. So to avoid consumption subsidization, I'm going to impose a no deficit condition for the seller. Okay? So the no deficit condition for the seller is just that monetary payments from the buyer to the seller are going to be non-negative. Okay? And this is obviously a normalization. I could have think of not just ex post deficit free, but ex ante, for example. Okay? So this is what I think of implementable without deficits in this context. Okay? I could also add individual rationality here, and that's what you think it is. So the mechanism is individually rational if it never requires the buyer to pay more than the value for the alternative. Okay? So as I said, direct mechanisms allow me to explain the constraints very simply, but I'm going to shift, and instead of working with direct mechanisms, I'm going to work with a nonlinear pricing scheme. Okay? A bit of notation. F inverse A is the subset of types that the mechanism assigns, that are assigned A under the mechanism, under the allocation rule F. Okay? So this is the set of types that get A under the mechanism if they follow the recommendation of the mechanism. And the first lemma tells me that if the direct mechanism is incentive compatible and budget feasible, then there must be a price, a unique price for A, such that the price for A is equal to any transfer of those types, okay, for all types that select A under the allocation function F. And the proof is very simple. So suppose it's not the case. Suppose that two types, VB and V prime, B prime, B prime, are allocated A under the mechanism F, but they pay different amounts, okay? Then, because of budget feasibility and incentive compatibility, the guy who pays the most has a profitable deviation. And that contradiction gives me the result. Okay? So it's a two-line proof. So I'm going to focus on, from now on, I'm going to work with nonlinear prices. F, the allocation function F, is called implementable without deficits if there exists a pricing function P such that the selling mechanism FP satisfies incentive compatibility, budget feasibility, and the no deficit condition. And if I impose individual rationality, I'm going to call that mechanism an acceptable mechanism. Okay? So far, I have just taken care of minor things. So let me tell you what the meat of the problem is, what the meat of our contribution is. Okay, and these are in the next three slides, you'll see what our contribution really is. I hope. So fixed allocation F. I'm going to define three things. The first thing is going to be the budget level for alternative A. The budget level for alternative A is the minimal budget of all types that select A under the allocation function F. So consider all types that get A, take the infimum of the budget, that's the budget level for A. And notice that it acts as an upper bound on prices that you can use respecting budget feasibility. Okay? So that's the first thing. The second thing is the buyer's unrestricted incremental value between A and A prime. And if you know Ricky's work, this should be familiar to you because he and others have used this a lot. So the unrestricted incremental value between A and A prime is the infimum of the valuation difference between A and A prime for all types that are allocated A under the allocation function F. Now notice that this doesn't take into account affordability. So it may be that for some types, they cannot afford A prime. Okay? So to take into account affordability, I'm going to introduce a new incremental value that I call the restricted incremental value. So the restricted incremental value between A and A prime, denoted delta R A prime, is the infimum of the valuation difference between getting A and getting A prime for all types that select A under the allocation function F and such that the budget that they have allows them to potentially afford A prime. So B has to be greater or equal the budget level for A prime. Okay? Now, you may think that this is just a technical definition or a technical difference, and let me tell you, let me try to convince to you that this actually has economic content. Okay? So let's assume, why not, that the budget for A is strictly less than the budget for A prime. Okay? Now, because all types that buy A prime have a budget above beta A, there is no difference between the restricted incremental value between A prime and the unrestricted incremental value between A prime and A. So I have this equality here. Okay? Let's consider more interestingly the other case. So I keep assuming that beta A prime has, so the budget level for A prime is above the budget level for A. Think first of the left-hand panel, okay? So as before, in the horizontal axis, I have the valuation difference between getting A and getting A prime. So think of A as public housing, where I live, and think of A prime as the mansion by the beach that Claudio has in Sydney, okay? These points represent types that get allocated public housing under the allocation function f. And what this tells you is that the mechanism doesn't discriminate based on how much money you have, right? So if Claudio and I value public housing the same, despite of him being 5 times richer than I, we both get allocated public housing. Okay? And in that case, there is no difference between the restricted and the unrestricted incremental value. Go to the right-hand panel. In this case, so no type that is rich gets allocated A prime. So public housing is restricted for low-budgeted guys. Okay? And because of this, because there is no type that can buy A prime, no type that is allocated A that can buy A prime, the unrestricted incremental value is plus infinity, because it's the infimum of an empty set. Okay? In the final panel, in the bottom panel, the mechanism, so the designer, the government, is choosing, the government lets you buy public housing even though you are rich, but only if you value public housing a lot. So in this case, if you don't value public housing much and you are rich, you don't get to buy A prime, but you do get to buy A prime even though you are rich if you value A prime, if you value A sufficiently high. So in this case, the restricted incremental value between A and A prime is finite and is strictly above the unrestricted incremental value. Okay? And all these cases can happen, and whether they happen or not is a decision that the principal, that the designer makes. So the designer makes the decision of being here, here, or here. Okay? And that will affect the difference between the restricted and the unrestricted incremental values. Yes. So in the next slide, I still have beta A prime strictly greater than beta A, but now I'm considering the incremental value between A and A prime. In the previous slide, I considered the incremental value between A prime and A. Exactly, yes. Yes, yes. Okay? So again, the main takeaway from this slide is that the difference between restricted and unrestricted incremental value is just not technical. It has economic content. It is an instrument of design of the principle. Okay? And you'll see what I do with those. Okay, so a preliminary result, let FP be a budget feasible selling mechanism. The first part of the proposition says that if FP is incentive compatible, then the restricted incremental value between A and A prime acts as a bound for the price difference between A and A prime. So I have a necessary condition. Okay, so remember that restricted incremental value is related to a necessary condition for incentive compatibility in this case. B says that if the unrestricted incremental value between A and A prime is above the price difference between A and A prime for all alternatives A prime, then the mechanism F, P is incentive compatible. And again, notice that here I have a sufficient condition using the unrestricted incremental value. And then you can ask me, can this be bridged? And the answer is no. Okay? So I have counterexamples in the paper, but let me first give you the proof, because everything I told you, I'm lazy, so everything that I do is very simple. Okay? So let's prove A. Suppose that, so the case where delta R is infinity is trivial, so I forget about this. Let's suppose that you have delta R, the restricted incremental value between A and A prime, to be minus infinity. Okay? Now, because it's minus infinity, I know that there is some type in the set of types that select A, but can afford A prime. So take one, fix epsilon greater than 0. There is a type V, B that is assigned A under allocation F, and such that his budget is above the budget level for A prime. Okay? Moreover, it must be the case, by the definition of the restricted incremental value, that the value difference between A and A prime is less than the restricted incremental value plus the delta. Okay? Now, by budget feasibility, I know that the price for A prime has to be below the budget level for A prime. Okay? Otherwise, I would be violating budget feasibility for at least one type. So it follows that this type can afford to buy A prime. So A prime is an affordable deviation. And on the other hand, rewriting the incentive compatible constraints, I notice that, the price difference between A and A prime has to be below the value difference between A and A prime, and that is below delta R plus epsilon. So take epsilon to 0, you get the result. Okay? Very simple stuff. No heavy machinery. So let me prove, I think I have time to prove B. So suppose on the contrary that the allocation function satisfies this inequality with P, but F, P violates incentive compatibility. Then I can find two alternatives, A and A prime, and a type, VB, that selects A under the allocation function F, but has a profitable and affordable deviation to A prime. Because it's a affordable deviation, I know that because the mechanism satisfies budget feasibility, I know that the difference between valuation and price is greater than minus infinity. And the second inequality holds because this is an affordable and profitable deviation for this guy. And I rearrange the equations, and I notice that the unrestricted incremental value has to be weakly less than the valuation difference between A and A prime, and this must be strictly below the price difference between A and A prime. Okay, and that contradiction gives me the result. Okay? So, remarks before moving on. Working only with restricted incremental values is not sufficient. Working with unrestricted incremental values is not necessary. Okay? And we have counterexamples in the paper. So we cannot bridge the gap between unrestricted and restricted incremental values when budgets are private. On the other hand, when budgets are public, the condition applies. So when the budgets are public information, the restricted and the unrestricted incremental values are the same because I only have one budget. Yeah, because it's public information. Now you would think that with public budgets we can just rewrite Roche's condition, cyclic monotonicity, to get the results, and it's not true. And Ricky knows it, but probably some of you don't. So let me give you an example for why the typical graph, the typical cyclic monotonicity graph doesn't work. Okay? So let's suppose that the seller has two alternatives, A and A prime. and the buyer has a single budget. So this is a public budget environment. V1 is equal 5. And the buyer has two valuations, V and V prime. And the values are here. So V gives 20. So under V, you value A 20, A prime 10. Under V prime, you value A 10 and A prime 0. Okay? And in the allocation function that I want to work with, the type V gets A, the type V prime gets A prime. Okay? Now, as I told you, I have public budget, so there is no difference between restricted and unrestricted incremental values. So the unrestricted, the incremental value between A and A prime is 10. So it's the difference between 20 and 10. And the restricted incremental value between A prime and A is minus 10. This is the difference between 0 and 10. So if you go to cyclic monotonicity, you can see that the only cycle has 0 length. Because I go from A to A prime, that's 10. I come back, A prime to A, that's minus 10. The length of the cycle, of the unique cycle, is 0. So following the literature, you would say this function is implementable without deficit. It turns out it's not. Okay? Because of the incentive compatibility constraints, I know that the price difference between A and A prime must be 10. On the other hand, the feasibility condition tells me that the price for A must be at most 5. And the price for A prime must be non-negative. And if I put this together, I have a violation, a contradiction to this equality. Okay? So I need to come up with a new network, and this is what Juan and I did. Okay? So I'm going to work with a new allocation network, H, that has a set of nodes N and edges E. Okay? The set of nodes is going to be A, the set of alternatives, union A naught. So for now, think of A naught as a dummy, but when we impose individual rationality, A naught will give you, will play a role there too. So this is my graph: A prime, A double prime, and A naught. Okay, these are my nodes. I have a set of directed edges: E1 union E2 union E3. So let me go slowly here. E1 is the cross product A to A. So it's the complete graph in the other world. Okay, in the standard world. So I have a complete connected graph between all the alternatives. Okay? That's E1. E2 is going to connect the alternatives to the sink of the network. Okay? So E2 contains edges from A to A naught. And E3 is used to close the cycle. So E3 connects A naught, the sink of the network, with the other edges. Okay? So I have a network, I have my edges, I need to impose values associated to those edges. And instead of talking about the length, I'm going to talk about maximal and minimal capacities. Okay? So every edge E is endowed with a minimal capacity, kappa lower bar, and a maximal capacity, kappa upper bar. Okay? For all edges in E1, so for all edges that are consisting of alternatives, the minimal capacity between A and A prime is going to be the unrestricted incremental value. The maximal capacity is going to be the restricted incremental value. That captures incentive compatibility, okay, with budget feasibility around the corner. Now, for all alternatives A to A naught, the minimal capacity between A and A naught is going to be equal to the maximal capacity between A and A naught, and it's going to be equal to the budget level. And that will capture budget feasibility. What about no deficit condition? I use the edges between A naught and A to close this. So I let the minimal capacity between A naught and A to equal to the maximal capacity between A0 and A, and that is going to be equal 0. Okay? So that's my graph. It has a minimal and maximal capacity, and I can show, using the previous example, why this allocation function is not implementable, right? You have so remember, in this case, unrestricted and restricted incremental values are the same because I have public budgets, so there's only one budget and it's 5, but I have a cycle of negative capacity. So A prime to A, that's minus 10, A to A naught, that's 5, the budget, A naught to A prime, that's 0, okay? So F1 is not implementable without deficits. So here are the two main results of the paper, a necessary and a sufficient condition for implementability without budgets. If the allocation function F is implementable without deficits, then the corresponding allocation network H contains no cycle of negative maximal capacity. That's necessity. Sufficiency tells you if the allocation network H contains no cycle of negative minimal capacity, then there is a pricing function P that implements F without deficits. And now we can construct P using the graph, using the allocation graph. Okay? So let me give you a couple of remarks before I move on. With public budgets, minimal and maximal capacities coincide, so we have a full characterization of implementability without deficits there, and I think that's a world. No, you do have paper. You do have a characterization result with public budgets. Yeah. So this. Single object. Okay. So this is a world first. Okay. So let me claim, unless Ricky disputes my claim, this is a world first. Okay. With private budgets, the gap between sufficiency and necessity cannot be breached in general. Okay, we do have counterexamples in the paper. And again, let me stress this, the difference between minimal and maximal capacities are not artificial. They have economic content. They are an instrument of the sign of the principle. Okay? Yes?
Maybe you just set it up, so I was thinking. So if there's a selection that is no negative cycle?
If there is, no. So you have to verify that,
no, I'm asking.
Excuse me.
So you have, think of the correspondence that you know.
Oh, no, I see. No, I use maximal and minimal.
I understand.
Yes.
Suppose you imagine that as a correspondence, and you ask yourself, is there a selection?
That I don't know. And you know the problem.
No negative
yes.
Cycle? That sounds like a conjecture.
It is a conjecture. The problem with that is that sometimes I have that delta R is plus infinity. And delta R is the restricted incremental value. So it's, I know what you mean, and I thought of that, and after scratching my head for some time, I realized that it wasn't as simple.
But just a second, if there's a plus infinity, where's the plus infinity?
So here it can be a plus infinity. It's a necessary condition.
Okay, but still that means it's selection. How does that affect this?
It doesn't mean that I can use any value between the minimal, the maximal, and the minimal and the maximal to implement.
You're saying that kills it.
Yes. So the interesting thing about this is that it's extremely subtle.
I'm not sure it's subtle, but that doesn't kill it. I don't understand your comment about the plus infinity. I'm sorry.
So what I mean is that in this, for the necessity part, you sometimes have that the negative maximal capacity is plus infinity.
I think that must mean that whatever that connection is, it's kind of irrelevant for any possibility of a cycle. If the selection thing is true.
Yes, again, from the top of my head right now, I don't remember exactly what the problem was with just taking a selection between the minimal and the maximal and use the selection. But it wasn't the case.
Oh, you think it's false?
I think your conjecture is false. I think your conjecture is false. Yes, I think your conjecture is. I remember trying to do that. So you think of revenue equivalence, for example, and you think of instead of the convexity, you use Lipschitz continuity, and you have that doesn't work here. as I cannot have, I don't have the counterexample in the top of my head, but I will double check. Yeah? 5 minutes. Okay. So let me jump to what I think is also really cool from this paper, and is that I get prices from the network. Okay. So the minimal capacity. Let me define first the minimal charge. C lower bar between nodes X and Y is the minimal capacity of the path with lowest minimal capacity. So it's the analog of the distance in the cyclic monotonicity literature. Similarly, the maximal charge between X and Y is the maximal capacity of the path with lowest maximal capacity connecting X and Y in my network. Okay? Now, as I said, in the sufficiency part, charges, I can use minimal charges to construct the pricing function that implements F. Okay? So if my network satisfies the no cyclic monotonicity, if my network H has no cycle of negative minimal capacity, I can use the charge between A and A naught and as the price for A. Okay? So that's sufficiency. For necessity, I don't have a tight result for all alternatives, but I do have a tight result for the world with two alternatives. So the general proposition says that if the pricing function P implements F, then the maximal charge between A and A naught is an upper bound for prices. Okay? Now, the result is tight if I have two alternatives. Let me move to the examples to show you how I work with this. Okay? So this is the picture that you had before, the example that I gave you. Let me try to implement an allocation functions here. And suppose that we first do something very simple, and it's to discriminate via budgets. Everyone that is rich gets A prime, everyone that is poor gets A. Okay? So I just map the negative, the minimal and maximal capacities in my network, and I see that here the maximal charge for A is just going from A to A naught by 5, so that's 5. And then if I want to compute the price for A prime, I go A prime, A naught, that gives me 10. And those are the prices that implement this allocation function F. Okay? That was really simple. I didn't need the network to give you those prices. But now I want to look at revenue maximization for this example. Okay? So even, you can do this by hand, which is how I did it. I don't have yet a methodology that allows me to systematically address revenue maximization. But by hand, you can show that in this case, the revenue maximizing allocation function is one that binds together this type, this rich guy, with all low budgeted guys. So all these guys receive A. These guys receive A prime. And again, I can just use the network to compute prices. The price for A is going to be the charge between A and A naught, that's 5. The price for A prime is going to be the charge between A prime and A naught, that's 10 plus 5, 15. Okay? And I can do comparative statics, and the exercise of comparative statics is nice because it allows me to tell you that suppose I'm the government and I decide to give everyone a subsidy of $3. And then you tell me, oh, that's going to be easy. So if you subsidize $3, if you give every type $3, then the seller can charge this $3, and that would be just a redistribution. It turns out that it's not the case. Because if you give everyone $3, the price is going to be bound by this guy. By this guy, who has a value for A of 6. Actually, this guy, sorry. Who has a value for A of 6. So you cannot charge these guys more than 6. So what you do is you kick this guy out. In this comparative exercise, comparative statics exercise, I assume that the low budget is not 5, as I did before, it's 8. And now the optimal allocation selling mechanism excludes this guy. Okay? So I can compute prices. Prices are now 8 for A because this guy is no longer constraining the price for A, and A prime costs 18. Okay? So again, this example highlights the fact that just transferring buyers' money it doesn't translate necessarily into higher revenue unless you change the allocation function. And this approach can take care of that too. Okay, so let me conclude. We study the design of deterministic selling mechanisms in a general setting, and again, I think that is not a handicap of the paper. It's valuable that we have a general result because then we can adapt this general model to different applications. We provide sufficient and necessary conditions for the allocation rule to be implementable without deficits. There is a subtle difference between incremental and unrestricted, but between restricted incremental values and unrestricted incremental values, and that difference is the design of the seller. And finally, we use a novel flow network approach to understand implementability, and our approach allows us to construct implementable prices as well. So a bit of promotion. In a second paper, we sort of use this technology to come up with a revenue equivalence result for a budget, for situations where budgets are private. And I think that's the first such result that there is. Okay? Okay, I'm done. Thank you.
So no deficit is like a minimum charge, common minimum charge for everyone. I don't have application, but just pure curiosity. If I have different minimum charge, so there's a negative, positive, but different for each type.
So what you would do is you would adjust. We haven't done that in the paper, but this is my conjecture, and it's an informed conjecture. What you have to do, if you allow transfers from sellers to buyers, you have to modify this number here.
Well, but depending on type. So it's just like budget is depending on type.
Yeah, it would be depend. So here it would depend on alternatives. So it would say everyone who buys A gets a subsidy of 5. Everyone who buys A prime gets a subsidy of 10. And it's incorporated in the network. It can be incorporated in the network. Yeah. So we haven't done the exercise of revenue maximization in a general setting yet. This is the second step of our research agenda. But I do believe that this methodology can be useful. Yeah. Okay. Thank you.